When you look at, say, a huge concrete bridge or a skyscraper, right, you don't really think about the small metal parts holding it all together.
No, not usually.
But these steel anchors, these things attaching structural bits to the concrete, they're absolutely critical. And it turns out there's a lot more going on with them than you'd initially think.
It really is fascinating. What seems like a simple setup, steel anchor in concrete involves some pretty complex physics. And for this deep dive, we're looking at some new research.
Right.
It digs into how the actual shape of these anchors affects the concrete they sit in, specifically how it relates to something called concrete cone failure when you pull on the anchor.
Exactly. We've got this paper from Fracture and Structural Integrity. The title's a bit of a mouthful. Parametric study on the effect of anchors geometry on the stress distribution and crack initiation direction in a concrete body.
Yeah, quite technical.
But the core idea is they use these advanced computer models to see the indivisible forces, basically. And parametric study just means they tweak things, right, like the anchor dimensions.
Precisely. They systematically change specific features of the anchor to see how stress patterns shifted in the concrete around it.
And our mission here, for you listening, is to kind of unpack this, to show how small design tweaks can really matter for the safety and strength of structures. Hopefully you'll have a few aha moments about the hidden engineering all around us.
Let's hope so.
Okay, so basics first. The paper mentions two main kinds of anchors.
That's right. You've got cast-in anchors, like the name suggests. They're put in place before the concrete gets poured.
Okay, set in the wet concrete.
Exactly.
Yeah.
Then you have post-installed anchors. These are put in after the concrete has hardened, usually drilled in.
Got it.
But the key thing, regardless of type, is that when these systems fail, it often starts in the concrete, not necessarily the anchor itself.
Interesting. So the steel anchor could be perfectly strong, but the concrete gives way. And this concrete cone failure the paper talks about, what is that exactly? It sounds pretty dramatic.
It can be, yeah. It's quite sudden. Imagine pulling hard on an anchor embedded in concrete. Concrete cone failure is when a cone-shaped chunk of the concrete just breaks away around the anchor head. It's a brittle fracture.
Whoa.
And it happens fast, leading to a major drop in how much load the anchor can actually hold.
Like a clean cone just pops out. And this study is looking at why that happens when you pull straight out on the anchor.
Precisely that. There are other ways anchors can fail, of course. The anchor might pull out, the steel might break,
Sure.
or the concrete could crack differently. But this research zooms in on that cone failure under a direct pulling or tensile load.
Right. So how on earth do you study something happening deep inside the concrete? You can't exactly stick a camera in there while you're pulling it apart.
Ah, well, that's where the computer simulations come in. They use something called the finite element method, FEM-M.
Okay.
Essentially, you build a virtual model of the anchor and the concrete, define their properties, and then simulate the forces. It lets you see the internal stresses.
A virtual stress test. Makes sense. The paper mentioned perfect adhesion between the steel and concrete in their model. What's that about?
Good point. So in their simulation, they assumed the steel and concrete were perfectly stuck together, no slipping at the boundary.
Like superglue.
Kind of, yeah. In reality, it's more complex, but assuming perfect adhesion is a common way to simplify the model initially. It helps isolate the stresses building up purely within the concrete itself.
Okay, I get that. And the model wasn't the whole block of concrete. They said something about a slice of a cylindrical specimen and using symmetry.
Exactly. Doing the math for a full 3D model is incredibly intensive. So they were clever. Since the setup is basically cylindrical with the anchor in the middle,
Right.
they figured the stresses would be pretty much the same all the way around, so they just modeled a thin wedge, like a slice of pie.
Ah, efficient.
Very. You get the crucial information without needing to compute the entire thing. Saves a lot of processing power.
And they use specific software. ANSYS Parametric Design Language, APDL.
Yeah.
Is that just the tool for building these simulations?
Yes, APDL is basically the programming language they used within the main ANSYS software. It lets you define the geometry, materials, the forces, everything very precisely.
Okay.
And it's great for these parametric studies because you can script it to automatically change dimensions and run the simulation again and again.
This is where I thought it got really interesting. They talk about critical distance, RC.
Yeah.
What is that? It sounds important.
It is. It comes from something called the theory of critical distances. The basic idea is that failure doesn't just depend on the stress at one single infinitely small point, like the very sharp corner of the anchor.
Okay.
Instead, it relates to the average stress over a small characteristic distance away from that point. This distance, RC, is linked to the material's internal structure, like tiny flaws or grain sizes where damage starts.
So it's not the absolute peak stress, but the stress in a tiny little zone near the corner. And they use values of 1 to 5 millimeters for RC. Why that range?
That range comes from looking at typical concrete properties. The paper mentions a way to estimate it based on the concrete's fracture toughness, that's its resistance to cracks growing, and its tensile strength, how much pull it can take.
Right.
For typical concrete, those numbers give you a critical distance somewhere in the low millimeters. So 1 to 5 millimeter covers that expected critical zone where a crack is most likely to kick off.
Fascinating. And they also plugged in specific material properties for the steel and concrete, didn't they? Young's modulus, Poisson's ratio.
Correct. You need those to make the simulation behave realistically, within the model's limits anyway. For steel, they used standard values, Young's modulus, around 210 gigapascals, showing how stiff it is.
Much stiffer than concrete.
Oh, yeah. And Poisson's ratio of 0.3, which relates to how it deforms sideways when stretched. For concrete, Young's modulus was about 23.5 GPa, and Poisson's ratio, 0.2. These numbers tell the computer how each material stretches and bulges under load.
Okay, so they've built their virtual test rig. What specific anchor shapes did they actually change and analyze?
They focused on a couple of key things. First, the anchor's outer radius, labeled R2. They tested 6 values from 20 up to 40 millimeters.
Okay, the width.
Yep. Second was the embedment length, lem, basically how deep the anchor goes into the concrete. They looked at a really wide range here, from 50 millimeters, quite shallow, up to 500 millimeters, very deep.
Half a meter, wow.
Yeah. And then, as we just discussed, they also looked at the results using those different critical distance values, RC, from 1 to 5 millimeters.
And other dimensions were kept the same to isolate these effects, things like R1, R3, layer mentioned in their table 1.
That's right. Standard scientific method, change 1 or 2 things, keep others constant, see what happens. It lets them clearly link changes in R2 and lem to changes in the stress patterns.
All right, so they're pulling out these virtual anchors, different shapes, different depths, and analyzing stress near the corner. What exactly were they measuring in those stress patterns?
They were really zeroing in on the tangential stress, sometimes called hoop stress. Think of the stress acting around the anchor point. They used the maximum tangential stress criterion, or MTS. The principle here is that cracks tend to start and then grow in the direction where that tangential pulling stress is highest.
So the concrete is most likely to tear where it's being stretched the most, sort of circumferentially. And that direction gives them the predicted angle for the cone failure.
Precisely. And the really cool part, the angle where their model predicted the highest tangential stress matched up really well with the angle people actually observe in real lab experiments, around 37.5 degrees.
Oh, wow. Okay, that's strong validation then. The model seems to capture something real.
It does. It suggests the model, even with its simplifications, is getting the fundamental crack initiation direction right.
So given this validated model, what happened when they changed how deep the anchor was embedded, the lem value?
Okay, this was a key finding. As the embedment length, lem, increased, meaning the anchor went deeper, the angle of that maximum tangential stress, they call it Themax, actually decreased.
Hold on. Deeper anchor, smaller angle.
Ugh.
What does that mean visually for the cone failure shape?
It means the cone gets flatter, more horizontal, instead of a steep, pointy cone coming out.
Right.
The potential failure surface spreads out more sideways, closer to the concrete surface, but over a wider area.
And why is a flatter cone better? Safer?
Well, think about it. For that flatter cone to actually break off, the crack has to travel a longer distance through the concrete to reach the free surface.
Wow, okay. Longer path.
Exactly. A longer crack path generally means more energy is needed to make it grow, offering more resistance. It might mean the failure is less abrupt, or the anchor holds a higher load before it happens.
Makes sense.
And they saw this angle max ranging from about 20 degrees for very deep anchors up to maybe 41 degrees for shallow ones, which fits well with experimental data too. For engineers, this is really useful. A flatter cone means more concrete has to fail.
Right, more material involved.
Which implies higher capacity. It could potentially influence how many anchors you need or what size, maybe saving costs while keeping things safe.
That does make intuitive sense. More concrete engaged means more strength.
Okay, what about the other variable, the anchor's outer radius, R2? Did changing the width matter?
It did, but its effect was more noticeable for the anchors that were already embedded quite deep.
Okay.
For the shallower anchors, changing the radius didn't make a huge difference to that failure angle, Themax.
But for the deep ones? Did making them wider make the cone steeper or flatter?
For those longer, deeper anchors, increasing the outer radius led to a slight decrease in that critical angle Femax, especially when they looked at the smaller critical distances, RC, closer to the anchor corner.
So, hang on. Similar to making it deeper, making a deep anchor wider also tends to nudge that failure cone towards being flatter.
That's what the results suggest, yes.
Yeah.
It also contributes towards that more favorable, flatter cone shape, requiring that longer crack path.
Interesting. So both depth and, for deep anchors, width play a role.
Correct. The conclusion was pretty clear. Both embedment length and the outer radius, particularly for those longer anchors, significantly influence that cone shape, generally pushing it towards a flatter angle as they increase.
So summing it all up, the big takeaway regarding anchor shape and concrete failure is,
The main point is that the anchor's geometry isn't just incidental. Its depth, and to some extent its width, if it's deep, directly affects how stress spreads out in the concrete. And that, in turn, dictates the likely shape and angle of that brittle cone failure if you pull hard enough.
and the trend is deeper is better, and wider, if it's already deep, is also generally better for promoting a flatter, potentially more resistant failure.
You've got it. Increasing lem, or increasing R2 on a long anchor, tends to lower that Themax angle, making the cone flatter. And they saw this consistently across those different critical distance values they checked.
It's really something how these dimensions affect fracture. Now, the paper is careful to say this focuses on crack initiation direction, using a somewhat simplified model. What else do engineers need to think about in the real world?
Oh, absolutely. This gives insight into where the crack starts. But real design needs to consider the whole fracture process, how much energy it takes for the crack to grow, that's fracture mechanics.
Right.
Plus, cost, how easy it is to install, maybe more complex models for how concrete behaves after it starts crapping, lots of other factors.
Makes sense. For anyone listening who wants to dive even deeper into the actual numbers and simulation details, did the researchers share their data?
They did, yes. It's publicly available in the Zenodo repository. They provide the DOI, the Digital Object Identifier, which is 10.5281 Zenodo.150832222.
Great.
So you can go look up the raw results there. And they also acknowledge their funding sources, the John Amos Kamensky Operational Program and the Czech Science Foundation.
Okay, so just to wrap up the key points for you. The shape of a steel anchor isn't trivial. How deep it goes, and sometimes how wide it is, changes how stress flows in the concrete and how it might fail. Deeper and often wider for deep ones seems to encourage a flatter, more stable failure cone when pulled.
Yeah, and hopefully this look inside the research gives you a bit more appreciation for the hidden engineering in everyday structures. These computer models are powerful tools for understanding forces we can't easily see, but are critical for safety.
Definitely. So here's a final thought to leave you with. Think about huge construction projects. How could optimizing anchor shapes based on this kind of detailed understanding improve the long-term safety and resilience of our infrastructure? Even small improvements could add up, right? What other questions does this make you think about regarding the materials and forces shaping our world?